Okay, we left off yesterday getting ready to talk about arc length. Not like an arc a boat, an arc like a circle. And this is ARC, not ARK. An arc is part of a circle. A central angle is an angle whose vertex is at the center of the circle. The length of an arc depends on the radius of the circle and the measure of the central angle, theta. So if I'm looking at this circle, I have the center, which is where the vertex is of the angle. Then the length of the arc depends on how long my radius is, so how long it is from here out to the edge of the circle. And that's going to be the same distance on this one as well, because my radius length is always the same. It never changes for a different point in the circle. On circles, it's always going to be the same for each part. Anyhow, then my arc is this length in here, which is determined by how wide this angle is along with the radius. Arc length can be calculated by considering an arc as a fraction of an entire circle. Suppose an arc in a circle of radius r has a central measure of theta. Since there are 360 degrees in a full circle, the arc is theta out of 360. So if my theta, or my angle, was 90 degrees, then this would be 90 out of 360, which would be 1/4 of the circle. If we think about a circle, I can draw a circle like this, and that's 360 degrees on the grid. So it'd be an angle that has an initial side starting here that goes the whole way around. That's 360 and ends up back here. If I was talking about theta equals 90, that looks like 1/4 of the circle. Yeah, going back to like maybe second or third grade with these fractions, where we have 1/4 of the circle now. So 90 degrees is in fact 1/4 of a circle. So my arc is going to be 1/4 of the length of the original circle. Now we're just going back to theta now instead of theta equals 90, just giving you an example. The circumference of a circle is 2 pi r. So that's how we find, that's our formula for circumference. C equals 2 pi r. So the length of the arc is the circumference, 2 pi r, times theta, divided by 360. So I'm doing circumference times my central angle measurement, theta over 360, or the whole circle. So circumference is 2 pi r times theta over 360. That will reduce to pi r theta over 180. So if I needed to find my arc length, that's all I would have to do. Put the radius in, or how long the side of the angle is, like here. You know, this is my radius, going from the center to the edge of the circle. So I would need my radius and my theta, and just plug it into the formula. So we can find an angle given an arc length. It says an arc in a circle has an arc length L, which is equal to the radius. So now I'm saying that my arc length, L, and we just came up with the formula for, that's cursive L, by the way, for those of you who don't know, lowercase. We just came up with my formula for that was pi r theta over 180. That was the reduced form. That came from here. and that's equal to the radius. So I'm trying to come up with a circle that was pretty terrible. Let's redraw those. Just want to illustrate what we're looking at here. I'm trying to come up with a circle where my radius, or this length here, is the same as the arc length, what this would be. So I'm needing this to be the same as these in here. So I'm just going to set this equal to r. Now I can start this one by doing pi r theta over 180 equals r. I can divide both sides by r. I said divide, and then I multiplied. So I'm going to divide both sides by r. This is r over r. So those cancel, and you're left with 1. This cancels out there. So I'm left with pi theta over 180 equals 1. Now I'm trying to solve for theta. I'm trying to figure out what angle measurement that would be that's going to give me this truth where I have an arc length the same as the radius. So I multiply both sides by 180 over pi. That all cancels out. I'm just left with theta on that side. And on this side, I have 180 over pi. So theta equals 180 over pi. And that's how much my angle measurement would be if I was looking for a radius that's the same length as the arc length. If I put 180 over pi in my calculator, I get 57 point, hold on a second, that's not true. Yeah, it is 57.29. So it is 57.29, or approximately 57.3 degrees. Now you might be wondering, wow, you did all that just to come up with this one time where the radius is equal to the arc length. This is going to turn out to be a important number in calculus and in pre-calculus. Unfortunately, we're supposed to have learned all this in pre-calculus, but that's okay. The angle that we just found in our second example leads to another unit used in finding angle measurement that's called a radian. So we keep switching our calculators to degree mode, and in some of your homeworks, I noticed that you didn't switch to degree mode, and I wrote that on there. If you go, speaking of which, if you go into your homeworks, you'll see that there's a thing that says edited under where yours is. After I grade the homeworks, I actually can write on them. So I'm editing your homework, telling you what you did wrong. Make sure you're going back and reviewing what you did wrong so you can understand. If you don't understand, get on the Google Meet with me and we can go over those old assignments. Anyways, now we're going to be going into radians. So this angle measurement is called a radian. The reason we do radians is because it simplifies a lot of our formulas in calculus and physics. Radians are used as a unit of angle measurement in both mathematical and scientific applications. Angle measurement in radians can be described in terms of the unit circle. That's going to be important to you, which is the circle of radius 1, centered at the origin, whose equation is x squared plus y squared equals 1. This is just the equation of a circle where the radius is 1. When an angle is in standard position, its initial side lies on the x-axis and passes through 1, 0. Its terminal side intersects the unit circle at some point P. Here is our circle. We can see that it goes through the point 1, 0 on the initial side. So our circle is at 1, 0. And then our ray opens up to where we get P, and we have this angle in here. So this is our actual angle measurement, everything inside of here. This circle is called the unit circle because it's all based off of the fact that this is at 1, 0. This point up here is at 0, 1, negative 1, 0, and 0, negative 1. So what a lot of calculus and trig is based off of. The radian measure of an angle is the distance traveled along the unit circle in a counterclockwise direction by the point P. So imagine, yesterday we talked about how our angles are dynamic now. We have that starting point where they start out on the initial side, and then it's moving counterclockwise. So as it moves from its starting point on the initial side to its final point on the terminal side of the angle, 1 radian is equal to 180 over pi degrees, which is about 57.3. If the vertex of an angle is the center, realize that's in your way. If the vertex of an angle is the center of a circle of radius r, then an angle of 1 radian intercepts an arc of length r. Movement along the unit circle is counterclockwise for positive measure and clockwise for negative measure. So remember, we are measuring angles. If it's opening going counterclockwise or this direction, it's going to be a positive measurement. If it's going the other direction, it's going to be negative. So if we look at this, on the unit circle, if I go around this far from this angle and travel counterclockwise around to here, it tells us that our angle went 3.75 radians, and our distance or our arc length is 3.75. Those are both the same when it's on the unit circle. So the distance traveled from going from this point all the way around to this one is 3.75, and that's what our angle measurement is. So you can see how that simplifies things. I wouldn't look at this and say this is a distance of 3.75 and it's 210 degrees. If I'm plugging both of those numbers into an equation, it makes it more difficult. Whereas now I can look at this, it's 3.75 radians for my angle, and my distance is 3.75. That's whenever we're going counterclockwise. If I was going clockwise, like on this one, my distance is 2, but you'll notice that my radians is negative 2. It's because directionally I went clockwise, which makes it a negative radian count. If I'm looking at where I go on a unit circle, if I start at the initial side and I go the whole way around and come back, we would have called that 360 degrees before. That is actually 2 pi radians. So 1 full revolution is 2 pi radians. So I would say that's just 2 pi. 3/4 of a revolution, or going counterclockwise around to here, is 3 pi over 2. Half of a revolution, starting here and going around to there, is pi radians. And 1/4 of a revolution is pi over 2 radians. And all this really makes sense if I start with the fact that the whole way around is 2 pi. If we're going back to that circumference thing, circumference is 2 pi times the radius, right? In this case, our radius is 1 because it's on the unit circle. So 2 pi times the radius, the whole length of this arc going around would be 2 pi. 2 pi times 1. If I'm looking at half of that, then I'm only doing 1/2 of 2 pi, which is pi radians. If I'm looking at 3/4 of that, it's 3/4 of the circumference. And then if I'm looking at 1/4, it's 1/4 of the circumference. So that's our intro to radians. I may, and I don't think I'm going to give you homework on this one. Just take the notes. Make sure you're understanding the concept of the radians, and I'll give you a homework assignment tomorrow as we get more in depth into radians and what they're going to do for us.